All right. So today I want to talk about an important theorem. It is a theorem that in some sense is the fundamental result that makes sense of how we develop the notion of cardinality for infinite sets. Recall that when we're dealing with infinite sets, and we want to ask how big these sets are, we can't just count them. They're infinite. So we have to define the sizes based on how functions act upon them. For example, as we know, two sets have the same cardinality if there's a bijection between the sets. But functions are complicated beasts, and there's no guarantee going in that things are going to work the way that we expect them to. The theorem that we talk about today, the Cantor-Schröder-Bernstein theorem, is going to tell us that cardinalities act like regular old numbers in a very important way. And this is what's going to make our whole theory of cardinality work and not collapse. Anyway, let's get to it. Let's start off just by stating the theorem. Let A and B be any sets. Assume that I have a map from A to B and a map from B to A, and both of these maps are injective. Then there exists a bijective map from A to B. Now this seems like a really straightforward statement, but it turns out it's extremely powerful. Let's recall a couple of definitions. We say that the cardinality of A is less than or equal to the cardinality of B if there is an injective map from A to B, and we say that the cardinality of A equals the cardinality of B if there is a bijective map from A to B. In this language, the CSB theorem says if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then A and B have the same cardinality. In practice, it is a lot easier to find an injective map in each direction than it is to write down a bijection explicitly. We'll show that in several examples later. There are 5 mathematicians who made significant contributions to this theorem, each in their own way. Cantor was the first to state the theorem, but did not provide a proof at that time. Schröder was the first to publicly give a proof, but it was discovered 6 years later that his proof was wrong. Note that this isn't necessarily bad, and we shouldn't be so critical. Even wrong proofs can give insight into results, and this was true in this case. Bernstein was the first to provide a correct public proof of the result, and in fact this was part of his PhD thesis. Interestingly enough, Dedekind generated a proof of the result shortly after Cantor's statement, but that proof was never widely publicized until much later. Finally, while Koenig did not produce the first proof of the result, he gave a much simpler and straightforward proof than existed at the time, and this is actually the basis of the proof that we give today. All of the mathematicians on this list made significant contributions to the foundations of mathematics. Many students of mathematics will know the names of Cantor and Dedekind, but Schröder and Bernstein, well, they have this theorem named after them at least, and while Koenig made significant contributions to the foundations of mathematics, he is now better known for his theorem in complex analysis, which is often used implicitly when computing contour intervals. We can see from the dates that 4 of these mathematicians were about the same age and were truly 19th century mathematicians. Bernstein was much younger and really was an early 20th century mathematician. Bernstein was on the faculty of Göttingen, but being Jewish, lost his positions when the Nazis came to power in 1933. He had some bit of luck to be traveling in the United States when this happened, and he remained in the States throughout the war. Okay, before we get into the applications of the CSB theorem, let's first go through an exercise. And this is an exercise in which we will show that the cardinality of the open interval -1 to 1 is the same as the real line. The way we're going to establish this result is by explicitly giving a bijection between the two sets. And here we go. So it turns out that there's a function called the hyperbolic tangent, abbreviated TANH and pronounced tanh, which is given by this combination of exponentials, e to the x minus e to the minus x divided by e to the x plus e to the minus x. We can see that this is a function that is continuous, and it is continuous because it's the quotient of 2 continuous functions and the denominator is never 0. We can check through a bit of a tedious calculation the derivative is always positive, and therefore the function is increasing. Moreover, when we let x go to infinity, we see that the e to the x term dominates on top and bottom, the ratio goes to 1, and when x goes to minus infinity, the e to the minus x term dominates, and the ratio goes to -1. The fact that this function is increasing means it's injective. The fact that it's continuous implies, using the intermediate value theorem, that it's surjective. Since this function is injective and surjective, it is therefore bijective. So in particular, we have proven, using calculus, that tanh is a bijection from the whole real line to the open interval -1 to 1. And by definition, this means these two sets have the same cardinality. Now let us generalize the last example a little bit, and we're going to show that the cardinality of any open interval is the same as the real line. So here's how we do this. Let's first define alpha of x to be the linear function b minus a over 2 times x plus b plus a over 2. That's obviously a linear function. Its graph gives us a line, and as long as its slope is non-zero, it gives a bijection. But of course, as long as b does not equal a, the slope is non-zero. In particular, this is a bijection from -1, 1 to ab. To check, if we plug in x equals -1, we get a, and if we plug in x equals 1, we get b. We just proved there's a bijection from the real line to the interval -1 to 1. So if we compose those two functions, alpha composed with f, that's a bijection from the interval ab to the real line. Again, by definition, this implies that the cardinality of the open interval ab is the same as the cardinality of the real line. Now we're going to state and prove a corollary of the CSB, and it goes like this. Any set of real numbers that contains an open interval has the same cardinality as the real line. Let's go with this proof. Let S be any set of real numbers, and assume that S contains the interval AB. Let us define F to be the bijection from the reals to the set AB that we established earlier. Since this is a bijection, it is injective. Now let the map G go from the interval AB to the set S be the inclusion map, where G of x is just x. This map is injective, and therefore G composed with F is an injective map from R to S. Since S is a subset of R, we can also consider the inclusion map from S to R, which is also injective. To summarize, we have an injective map from R to S and an injective map from S to R. By CSB, there is a bijection between S and R, and we are done. Okay, let us define B to be the following set. The interval -2 to 2, union a bunch of Cantor sets, all shifted by k so that they don't intersect each other, plus about 3 million other numbers just thrown in for some reason. And now we're asked, write down an explicit bijection between the reals and the set B. No, I'm not going to do that. I'm not going to do anything close to that. That's kind of ridiculous. There's no way somebody could write down such a bijection. However, it's easy to see that a bijection must exist. If we let F be the map from the reals to B, that's 2 tanh H, this is easily seen to be an injection from the reals to B. And then finally, since B is a set of real numbers, we can write down the injection that's just the inclusion map from B to R. Since there's an injection going each way, the CSB theorem tells us there exists a bijection, even if we could never write down the formula for it. Okay, now here's a really good example of how we can use the CSB theorem to prove something that would be very difficult to do otherwise. We're going to show that if we consider the set of all infinite sequences of natural numbers, that set has the same cardinality as the real line. The reason that we have to use the CSB theorem here is it's actually very difficult to write down an explicit bijection between these two sets. But we can cook up injections going in each direction pretty easily. So let's go ahead with the proof. Let's say we have a sequence n1, n2, up to nk, keep going, where all the n's are natural numbers. And now let us consider the binary decimal expansion constructed in the following way. We take n1 zeros, then add a 1, then n2 zeros, then add a 1, then n3 zeros, and then add a 1, keep going, and then nk zeros, and then add a 1. And notice that this is going to be a really long sequence, but since all of the n's are finite, we'll eventually get to every term in the sequence. And so we'll have sequences of zeros, and then a 1, and more zeros, and a 1, etc., etc. This is clearly an injective map. If you give me two different sequences of natural numbers, I'm going to put zeros or a sequence of zeros in different places. So that'll give me a different binary decimal expansion. Now we'll cook up a map going in the other direction. Let us imagine any binary sequence. So 0, point, B1, B2, B3, all the way to BK, keep going, where these are zeros or ones. Now let's start off by letting S be the empty string, and for every K, what we're going to do is append the set BK, 17. And what we're saying is, every time there's a binary digit of 0, we put 017 at the end of our string. Whenever there is a 1, we put 117 in our string. So for example, if we take the binary sequence 001, 001, then our sequence of integers is going to be 017, 017, 117, 017, 017, 117, and so forth. Now, of course, the 17 is a bit arbitrary. I just had to pick some number that's not 0 or 1. It's very clear from this sequence that this is an injective map. If you give me two binary sequences that differ at some place, then this sequence of integers is going to differ at exactly that place. So you can really think of the 17s as kind of little bookmarks that tell you where the digits are. Therefore, what have we shown? We have shown that there's an injection from n to the n to the closed interval 0, 1. There's also an injection from the closed interval 0, 1 to n to the n. Remember that the closed interval 0, 1 has the same cardinality as the reals because it's a set of real numbers that contains an open interval, and therefore it has the same cardinality as r, and therefore n to the n has the same cardinality as r. And we're done. Again, CSB is really nice here because writing down an explicit bijection here would be extremely messy and difficult. Okay, now we're going to start working on proving the CSB theorem. But first, a lemma. It goes like this. Let K be a map from the set A to the set B that is injective. If we restrict the codomain B to be exactly the image of K, then K as a map from A to K of A is invertible. To prove this, let's just note that K becomes surjective when we restrict the codomain. But of course, restricting the codomain isn't going to change the injectivity of K. So since K is now surjective and injective, it is bijective. A bijective function is invertible, and in particular, for any y in K of A, there is exactly one x such that K of x equals y. And this is because in the first place, K is injective. So let us define K inverse of y to be x, and this is the explicit inverse function of K. One small note, now note that the domain of K inverse is not B, but it's K of A. All right, we're going to get started on the proof. Let me introduce this geometric picture that gives us a good view of what's going to happen when we make the construction in our proof. Remember, we have the sets A and B. Here I'm representing A as a red square and B as a green octagon. Remember that F maps A to B as an injection, so that F of A is some subset of B. So we can represent that as a red square inside of B. Conversely, G maps B injectively into A. So we can represent the image of G as a subset of A. So we're representing these subsets in the following way. So again, if we take the set A, we can push it into the set B, and we see that it looks like a little subset inside there. And now here's what we're going to do. We're going to let the map G push the octagon back, but let's also keep track of where the red square was when we push it back to the left. And again, let's push forward with F. So we'll take the whole square with all of its structure and inject it back into B. And then again, apply the map G and put the whole structure back into the set A. Apply F, inject it into B. Apply G, inject it into A. And we keep doing this back and forth and back and forth and back and forth. And notice that we get this nested sequence of structures. Remember, the red corresponds to the set A and its images, and the green corresponds to the set B and its images. Okay, now for some definitions. Let us define R0 to be the set A minus the image of G. So it's going to be the red square minus the biggest octagon sitting inside of there. Let's let R1 be the smaller square inside of there. And remember, where does R1 come from? Is we push the square to the right by F, and then we push everything to the left by G. And that's how we got the smaller square. So R1 is G composed with F applied to the set R0. R2 is G composed with F applied to the set R1. And so on and so forth. We proceed inductively every set Rk. When we push it forward to the right and then pull it back to the left, we get Rk plus 1. Let us now define R to be the union over all k of those Rk's. And we're calling it R because it's the red points. So all the points that are red in this picture, even though there's this infinite cascade of all these sets, we call those the red points. Everything that's not red, we color green, and we call that set G. Remember these definitions? This is how we're going to proceed. Let's recall our definitions. Remember that R naught is A minus G of B. Rk plus 1 is what we get when we take the set Rk and push it to the right and pull it back to the left. And finally, the green points are all the points that are not red. Note that by definition, G of B is a subset of G, because remember, R naught was A minus G of B. Now, remember, by assumption, G is injective, but it's not necessarily invertible. But remember our lemma, by restricting the codomain of G, we can make it invertible, effectively. So G that maps from B to G of B is going to be invertible. So it makes sense for us to define G inverse with domain G of B. So now we're in a position to define this map H. That's going to be our bijection. H is going to be defined as follows. For any red point, H will be f of x, and for any green point, H will be G inverse of x. And again, let's recall, remember F and G were the maps we were given that were themselves injections. We constructed G inverse by restricting its codomain, and now we're defining H piecewise. Okay, now we're going to prove that H is injective. And we start by assuming that H of x equals H of y, but let's note that there are three cases. The first case is it's possible that x and y are both in R. Well, if x and y are both in R, then H is F, so H of x equals H of y implies f of x equals f of y. Remember that f is injective by assumption, and therefore x equals y. The second case is when x and y are both in G. Remember, if x and y are in G, that means H equals G inverse. So H of x equals H of y implies G inverse of x equals G inverse of y. Apply G to both sides of this equation, and we get that G of G inverse of x equals G of G inverse of y, but of course G of G inverse of x is x, and G of G inverse of y is y, and therefore x equals y. Now finally, let's consider the case where x is in R and y is in G. If H of x equals H of y, this means f of x equals G inverse of y. Let us apply G to both sides, giving us the equation G of f of x is G of G inverse of y, which is y. What does that tell us? That tells us that y is G of f of x. But remember the construction of R. For any point x in R, by definition, if x is in R, it's in one of the Rk, and so G composed with f applied to that point puts it in Rk plus 1, so it's back in R. Basically, what we've shown is that if x is in R and H of x equals H of y, then y must also be in R. Therefore, this third case can't happen. And as such, we have proved that x equals y. And of course, since we started by assuming H of x equals H of y, and then we deduced that x equals y, this is exactly the proof that H is injective. Okay, now let us prove that H is surjective. Remember what that means. We need to show that if we choose any y in B, there is some point that maps to B under H. So let y be in B. Let x equal G of y. There are two cases. The first case is x is in G. But notice that if x is in G, then H of x is G inverse of x. X was G of y, so that's G inverse of G of y, which is y. And there you go. That's a point that maps to y under H. The case where x is in R is a bit trickier. Let's go through the logic. Let's assume that x is in R, then x is in Rk for some k. Now note, k must be positive. X cannot be in R naught, because by definition, x is in the range of G, and R naught was A minus G of B. So x is in some Rk for k 1 or bigger. Now remember, Rk, if k is bigger than 0, was defined to be G composed with f applied to Rk minus 1. X is in that set. Therefore, there is some z in Rk minus 1, with g of f of z equals x. Now what do we have? X is g of y, and x is g of f of z. And remember that g is injective, therefore y equals f of z. Since z is in R, f of z and h of z are the same by definition, and therefore h of z is y. So note that in either of these two cases, there's some point that maps to y under h, and we're done.